Welcome to PLCs for Beginners. This course is recommended as a prerequisite to more advanced training, but it can also be helpful if you simply want to learn basic concepts. This course covers the following topics: PLC Overview, PLC Hardware, Numbers, Codes, and Data Types, Inputs and Outputs, SIEMENS S7 Modular PLCs, PLC Programming Concepts, Basic Ladder Diagram Programming, and Basic Function Block Diagram Programming. The focus of this course is on PLC concepts and terminology and not implementation knowledge and skills. This chapter covers the following topics: PLC Overview, PLC Hardware, and Numbers, Codes, and Data Types. Completion of this chapter will help you learn important PLC terms and develop an understanding of basic PLC concepts. Most factories contain dozens or even hundreds of machines, from the very simple to the complex. Some are still operated and controlled only by skilled workers. However, most complex machines rely on programmable logic controllers, PLCs for short. A PLC is an industrial computer that is used to control machines and processes. PLCs differ from office computers in the types of tasks they perform and the hardware and software they require. While the specific applications vary widely, all PLCs get inputs from switches and sensors, make decisions based on a stored program, and control outputs to automate machines and processes. Before PLCs were invented, machines were often controlled by electromechanical devices with complex wiring. This approach is called hardwired control. Hardwired control is still used for simple tasks, but for larger applications it is difficult to design, install, and maintain. Because tasks performed by PLCs are controlled by software and internally stored values, use of PLCs offers exceptional flexibility. As a result, PLCs are now used to run almost any industrial application, and almost every new machine that comes into a factory has a PLC controlling it. Consequently, many industrial jobs require knowledge of PLCs. The very first PLCs were designed for use in the automotive industry in the late 1960s. Prior to that time, control of an auto assembly line relied heavily on electromechanical relays, contactors, timers, and related devices. Every year, as design changes were made to different car models, these circuits had to be rewired. Rewiring circuits was a complicated and time-consuming task, and even when the relays performed well initially, the wear on all those physical contacts resulted in costly maintenance. Additionally, as manufacturing processes became more and more complicated, more relay circuits were needed. This resulted in even greater cost and complexity. Because the hardwired circuits replaced by PLCs used control circuit diagrams referred to as ladder diagrams, early PLCs used ladder diagram software programs, sometimes referred to as ladder logic, to make it easier for someone familiar with control circuits to program a PLC. Unfortunately, every manufacturer had its own version of ladder diagram programming. This variation in programming grew as PLCs were developed to handle a wider range of tasks. Today, most PLCs can still use ladder diagram programming, but the IEC 61131 International Standard now defines this programming language. This same standard also defines other types of programming languages available for PLCs so that they can be used for the most complex applications. In addition, even a small PLC can easily outperform hardwired electromechanical circuits. Most PLCs have a modular structure. Some PLCs have a block-type modular structure, but the majority have a traditional modular structure. Despite their variation in appearance, modular PLCs have a similar organization which includes the following components. The central processing unit, CPU, is the brains of the PLC. The CPU stores and runs the user program. The input-output system, often referred to as the I/O system, includes modules with I/O channels that connect to input devices such as switches and sensors, and output devices that are controlled by the PLC. A programming device is used to load the program to the CPU memory. The programming device is usually an industrial personal computer with software that allows you to create and modify PLC programs. The programming device is only connected to the PLC when it is needed. Although not part of a PLC, one or more human-machine interfaces, HMIs, are often connected to a PLC to allow factory personnel to monitor or alter a machine or process. I/O devices are sometimes the same as devices used in hardwired control circuits, but the relationship of these devices is determined by software referred to as the user program, which is stored in the CPU. This program is executed repetitively as part of a process referred to as a scan. After startup, a PLC scan includes the following sequence of operations. The PLC reads the statuses of input devices and records this information in its memory. The CPU executes the user program and changes internal memory values as needed. The CPU performs internal diagnostic and communication tasks. The CPU sends updated status information to output devices through the I/O system. This process is repeated continuously as long as the CPU is in the run mode. The time required for a scan depends on the capabilities of the CPU, the size of the user program, the number of I/Os, and the amount of communication required. However, because PLCs are very fast, a typical PLC scan is measured in milliseconds. This means that the PLC response time from reading an input to reacting by changing an output is also very fast. Input devices are usually switches or sensors that send electrical signals to the CPU through input channels on input signal modules. Similarly, output devices receive electrical signals from the CPU through output channels on output signal modules. These output devices are sometimes called actuators and are used to control a machine or process. PLCs have two broad categories of I/O. Digital I/O and analog I/O. Digital I/O devices, also called discrete I/O devices, are either on or off and are connected to digital I/O channels. Analog I/O devices use variable voltage or current signals and are connected to analog I/O channels. Analog I/O is used in applications where variable quantities such as temperature, pressure, rate of flow, etc. are being controlled or monitored. A central processing unit, CPU, is the brains of a PLC. The CPU stores the user program, I/O status bits, and other data. It also repetitively executes the PLC scan as previously described. As part of this scanning process, the CPU receives input information from input channels and sends output information to output channels. Simatic S7-1200 CPUs have a small number of I/O channels in the same housing. Most of these CPUs also have the capability to connect to I/O signal modules for additional I/O channels. Most other Simatic PLCs have all I/O channels on I/O signal modules. Both S7-1200 and S7-1500 CPUs have one or more communication connections referred to as ports. A communication port is designed for a specific type of communications. When a different type of communications is required, or when additional communication ports are required, one or more communication modules are used. Digital input devices provide an on or off signal to a digital input signal module in response to an operator input or a change in condition in a machine or process. The input device may operate on direct current DC or alternating current AC, and the voltage and current level is dependent on the type of device. A digital input signal module converts this value to a low-level DC signal that represents the on or off condition of the input device. For each digital input device, the on or off signal is stored in the CPU. Analog input devices provide a variable voltage or current to an analog input signal module. This variable voltage or current represents a condition in a machine or process such as temperature, pressure, vibration, rate of flow, weight, fluid level, etc. An analog input signal module converts each current or voltage value to a low-level DC signal and sends it to the CPU. For each analog input device, the latest value received from the device is stored as a number in the CPU. Digital output devices are turned on or off by signals from digital output signal modules. For example, an indicator light on an operator panel may be turned on to indicate that a machine is running. Often, however, the digital output device is used to cause a change in a machine or process, such as starting or stopping a motor or pump. Analog output devices receive a variable voltage or current signal from an analog output signal module. For example, an analog meter on an operator panel could be used as an analog output device to show a condition in a machine or process. Often, however, an analog output device is used to control a machine or process. For example, analog outputs from a PLC could be used to control AC drives, which in turn control pumps that fill and drain a storage tank. Input and output devices are often used to interconnect panels with lights and switches to one or more PLCs so that operation and maintenance personnel can monitor and control a machine or process. Increasingly, human-machine interfaces, HMIs, are also used for similar purposes. HMI panels range in capability from simple keypad devices to panels with the ability to graphically display an entire process. An HMI can also be a mobile device that allows freedom of movement for operation or maintenance personnel. A programming device is often a personal computer, PC, with software that enables it to program a PLC. Often an industrialized PC is used so that it can function reliably in a factory environment. The programming device frequently has additional functionality depending upon the software used. For example, a programming device running Siemens Totally Integrated Automation Portal (TIA Portal) software is used in all phases of the design, operation, and maintenance of systems that include PLCs, HMIs, PCs, electronic drives, and related devices. There are multiple ways to program a PLC. At one time, PLC programming languages varied with the PLC manufacturer. In general, however, PLCs manufactured in recent years are programmed using a language defined in an international specification, IEC 61131. Two of the programming languages defined in this specification are ladder diagram, LAD, and function block diagram, FBD.